Next up, we have what's called the quotient rule. And similar to the product rule, the quotient rule is used when we have a certain kind of division where we can't easily simplify the function, right? And again, the word quotient is just a fancy word for fraction, right? So here is the setup for the quotient rule. So suppose f of x and g of x are differentiable, right? And one more thing. Now, since we're going to be talking about a quotient or a fraction, whatever we put in the denominator, we have to make sure that it's not zero. So we're going to make the assumption that g of x is not zero. So in addition to assuming that these are both differentiable functions, I'll say, and g of x is not equal to 0, right? So that's where we're going to start off. Now let's define the quotient of f and g, right? So we're going to let y be equal to f of x over g of x. And we want to know, again, suppose this is a type of fraction that we can't reduce it or simplify it to something that to which one of our easier rules or simpler rules would apply, right? Or what if we just want to leave it in this particular form and figure out how to compute its derivative, right? Once again, if we want to do that, we have to turn to the limit, right? So now this again will be the limit as h approaches 0, and wherever there's an x in our function, we have to replace x with x plus h. So now it's going to look like this: f of x plus h over g of x, and then I have to minus the function, which is now f divided by g, so f of x divided by g of x, and all of that still has to be over h, right? So this is our limit definition. This is how it's set up when we have this quotient, this fraction, all right? Well, we typically don't like to see fractions within fractions. So we're going to have to do something to clear these fractions. And one thing we can do is to multiply the top and the bottom by a certain quantity. So I'm going to multiply the top by the common denominator here. And the lowest common denominator here would be the quantity, well, g of x plus h times g of x. So I'm going to use that to multiply the top. But if I do that, I also have to use it and multiply the bottom. So I'll have to put the same quantity down here. Again, I guess I don't need the square brackets, but just kind of emphasizing that the h is going to multiply this, and then these two fractions will multiply this, right? So what does it look like when we do this simplification, right? Or, well, you might not think it's a simplification, but at the very least, we're going to write this in a more standard way instead of having one fraction inside of a larger fraction. So we'll have the limit as h approaches 0. So if I take this product and multiply the first fraction, the g of x plus h will be reduced. So I'll be left with f of x plus h times g of x. So let's write that down. F of x plus h times g of x minus, now when I take the second fraction and multiply what I have in blue, the g of x will be reduced. So I'll be left with f of x times g of x plus h. So I'll have f of x times g of x plus h, and then at the bottom, I'll just have h times this, right? So I'll have h times g of x plus h times g of x. Okay, so we've gotten rid of the fractions, but now we have multiple factors in the top and the bottom. So what do we do here? So we would tend to glance and see, okay, do we have any common factors? Anything that we can factor out? And there's nothing in common, right? So this is where we're going to do another one of those tricks. Like we need to add and subtract something in the numerator that will allow me to factor by grouping. That was the trick that we used when we derived the product rule, and we're going to learn from that and try to add and subtract something here. So what I'm going to do is I'm going to subtract f of x times g of x from this and then add it back in, right? So let's do that. So this is going to be f of x plus h times g of x. So this is the extra term that I'm going to do subtract. So f of x times g of x, and then add that same term back in. So plus f of x times g of x. So essentially what I've done is I've added 0, right? And then minus f of x times g of x plus h. All right, so that's the numerator. And what we're going to do, based on what happened when we derived the product rule, we're now going to look for common factors that will allow us to factor by grouping. And I think you can see them. So here is the factor that we can factor out of the first two terms. They have a g of x in common. And then look at the last two terms. They have an f of x in common. Right? Not only that, but look at what's going to be left for instance, when I factor out what I have highlighted in blue there, or boxed off in blue. I'm going to have f of x plus h minus f of x, right? And so we're seeing already our difference quotients. And similarly, out of the last pair, we'll have a g of x minus a g of x plus h, right? Now that seems a little bit different. That one seems switched, right? But we'll be able to handle that, right? So this is what we're going to do. So is equal to, and then I have the limit as h approaches 0. So factor out the g of x there. So we'll have g of x, and then again in square brackets we'll have f of x plus h minus f of x. And then factor out the... Now what I'm going to do something a little bit different, because I want to see like g of x plus h minus g of x. So I want this sign to become positive, and I want this sign to become negative. So what I'm going to factor out, and this is a little bit different than it was in the previous case, but I'm going to factor out a minus f of x. And then what do we have to put in parentheses? Well, since this one has the minus f of x in front of it, I can write g of x plus h first. So I can put this here. Right? Now, this one has a plus f of x. But if I factor out a minus f of x, I have to put another minus there so as to balance this, to make sure that this product ends up being positive. So I have to put a minus g of x, right? So that's what it looks like when we factor out the common factors out of the first pair and then the last pair, and then at the bottom we still have this h times g of x plus h times g of x. All right. So now what we're going to do is I am going to write this as, now there are several ways that it can be written, but ideally we want to get those difference quotients, right? So we want to get those difference quotients where we have this over h and then this over h. So essentially what I'm going to do is, in fact, let me do an extra step here so we can see what's going to happen. I can write this as g of x times f of x plus h minus f of x all over h, right? And then minus f of x, and then in square brackets my g of x plus h minus g of x all over h, and then all of that is divided by h. Well, actually, no more h, because I have that in the denominator here already. What's left in the denominator is g of x plus h times g of x, right? And I'm taking the limit of all of this, right? But we have all the limit properties. Then these limit properties, this is what they say. I can take the limit of the g of x by itself and multiply the limit of my first difference quotient for f. So the limit as h approaches 0 of f of x plus h minus f of x over h, and then keep the minus sign, and then the limit of f of x. Right, so your limit as h approaches 0 of f of x, and then times the limit of that difference quotient. So the limit as h approaches 0 of g of x plus h minus g of x all over h. And then, remember, my limit properties also work under certain conditions. If I don't have a 0 in the denominator, they also work down here. So I'll have to have the limit as h approaches 0 of g of x plus h, and then times the limit as h approaches 0 of g of x. Wow, right? But that's what we have, right? So let's go through. There's 6 limits here, and we can simplify all of them quite a bit. We saw this previously when we derived the product rule. When you're taking the limit as h approaches 0 of something that doesn't have h in it, then you treat it essentially as a constant, right? Because it is not going to change because it's not affected by h. So the g of x comes down. Times. This is our difference quotient, or the limit of this difference quotient is our derivative of f. And we know that exists because we're assuming that the function is differentiable. So this is f prime. And then there's a minus. Bring the minus down. The same argument that I gave for g, or the limit of h as h approaches 0 of g of x, it also applies as h approaches 0 of f of x. Again, this does not involve h, so it does not change as h approaches 0. So we have an f of x there. And then this difference quotient is the derivative of g. So that's g prime. And then this is all over, what do we have here? By continuity, right? As h approaches 0, this approaches g of x. Essentially, we can evaluate it. And we replace h with 0, and we have g of x there, times, and then here again we have the exact same limit as we did in the numerator right here. And again, this does not involve h, so the g of x stays the same. And now we're left with this rule. And let me just write one more thing. So, and I'm going to write it like this, and this is again the way I like to say this quotient rule. So it's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared, because I have g of x times itself. All right. So now let's, as always, let's write down the summary, right? So if we now have a quotient of two differentiable functions where the denominator is not equal to 0, then that quotient is differentiable, and this is the formula that gives you its derivative. So then dy dx is equal to, and I'll just restate it again, and this is why I refer to top and the bottom. So I'm talking about what's the function in the top of the fraction, what's the function in the bottom of the fraction, and I say it like this: it's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And this is the famous quotient rule, right? So this is our quotient rule, and it gives us a specific formula for differentiating quotients, all right? Let's do a couple examples, for this, what I'm going to do is essentially one function, but not only are we going to compute the derivative using the quotient rule, but let's then use the derivative to find the slope of the tangent line, right? So let's take a look at this example to see how it all works, right? And so let y be, so let's say our function is e to the x minus 2x, and it's over x squared plus 3x plus 1, right? And what we want to do is to find the equation of the tangent line to this function at x equals 0, all right? So that's what we have to do. Now, if we're going to find an equation of the tangent line, again, there are two things that we need. We need the ordered pair that the tangent line is going to pass through, and we need to know the slope at that point, right? So the ordered pair, the point, that's pretty easy, because if I know the x value, plug it into the original function, and that will give me the y, right? So if I have, when x is equal to 0, y is equal to, well, let's evaluate this. E to the 0 is 1, and then minus 0 over 0 squared plus 3 times 0 plus 1. So I end up having 1 over 1, which is 1. So the tangent line passes through this point. Now comes the calculus part. In order to find the slope of the tangent, we need the derivative. So now, because I have a quotient here, I'm going to use my quotient rule. All right, well, let's see what happens. So let's write down dy dx, or if you want to use y prime, either way. So the quotient rule, and again, this is how I say it out in words. It says you take the derivative of the numerator, and I'll write out that kind of initial setup. So the derivative of the numerator times the denominator, and again, since that denominator has multiple terms, I want to make sure I use parentheses, and then minus the numerator, which also I'll put in parentheses, times the derivative of the denominator, and that's again your x squared plus 3x plus 1, and then this is all over the denominator squared. So that whole quantity squared. All right. So let's go ahead and simplify the numerator, because we have two derivatives that we have to write down, right? So again, the derivative of e to the x is e to the x. The derivative of minus 2x is minus 2. And then we have so that's a quantity. And then it's going to multiply what we have here. So we have x squared plus 3x plus 1. And then minus the top, which is your e to the x, minus 2x. And then the derivative of the bottom, or the denominator, is another quantity, 2x plus 3. And again, this is all over the quantity x squared plus 3x plus 1 squared. There is no need for us to expand all of this. It can be done, right? But really, in order to answer this question, to find this tangent line, what we need the derivative for is to find the slope at this point, right? And here's a useful notation. So for instance, if you use the y prime, obviously we can do this to indicate that we're going to plug 0 in. If we use the dy dx, this is how we indicate that operation. We have the derivative, and we have this vertical line, which means evaluated at, and then at the bottom here you put whatever x number you're about to plug in, right? So both of these are saying the derivative of the function evaluated at x equals 0, right? Well, let's evaluate it like term by term. So in the first pair of parentheses, we have 1 minus 2. In the second pair of parentheses there in the numerator, we have 0 plus 1 minus the third pair of parentheses, we have 1 minus 0. And then the fourth pair of parentheses, we have 0 plus 3. And then at the bottom, we're going to have 0 plus 1 squared, right? So let's carefully simplify this. And we end up with, so this is negative 1 times 1, so we have a negative 1 there, and then minus, it looks like 3, because this is 1 times 3, so minus 3, and then all over 1 squared, which is 1, so our slope comes out to be negative 4, right? So the slope of our original function is negative 4. We know the point. Let me scroll back up so you can see the point right there. 0, 1. So we have the point, we have the slope. Now we can use either y equals mx plus b, which is our slope-intercept form, or y minus y0 equals m times the quantity x minus x0. So I think you know my preference by now. So here's the equation of the tangent. So equation of the tangent line. It's y minus the y value, and that's equal to the slope times x minus the x value. And then we can convert this into the y equals mx plus b form by adding 1. So this is negative 4x plus 1. So that's the equation of the tangent line to this curve. But the key here is now that we have our quotient rule right there at the top, and this is what enabled us to find the derivative of this function. And as our functions get more complicated and they involve more operations, then there's the need to have more rules, right? And you might be wondering, how many rules are there? Well, there are a few more. There's one more in terms of a specific operation that we need to cover, And then after we establish those kind of general rules, we'll then look at, okay, how do we differentiate trigonometric functions, or how do we differentiate logarithmic and other exponential functions, and so forth. How do we differentiate inverse trigonometric functions, right? So very quickly we'll be able to have a set of rules that will allow us to differentiate any elementary function that we would have seen, right? So see you in those videos.